Let's start out today's class with reviewing the three right-hand rules. So the first right-hand rule that we covered allows you to find the direction of the force on a charge in a magnetic field or the direction of the force on a current-carrying wire in a magnetic field. So that's right-hand rule number one. Right-hand rule number two allows you to find the direction of the magnetic field being created by a current-carrying wire. And right-hand rule number three gives you the direction of the magnetic field created by a current loop. So a loop of wire carrying a current. Let's go through each of these three again individually just to reinforce what we've talked about. So right-hand rule number one, again, either applies when you're talking about the force, the direction of the force on a charge in a magnetic field, or the direction of the force on a current-carrying wire in a magnetic field. Remember that to find the magnitude of the force for any cross product, it's just the vectors, the magnitudes, times the sine of the angle between them. So the magnitude of the force is QVB sine theta, or the magnitude of the force on a wire would be ILB sine theta. Okay. So how do we do this? Well, again, remember that vector B and vector V define a plane. So the answer for the direction of the force is always perpendicular to that plane, perpendicular to each of the original two vectors. Again, first finger in the direction of the velocity, second finger in the direction of the magnetic field. Your thumb gives you the direction of the force. The key thing in applying this right-hand rule, by the way, is once you've got your first finger pointing in the direction of the V, you can't move it. All you can do is rotate your hand to get your second finger pointing in the direction of B. Your first finger still has to be in the direction of V. That's the common mistake students make. When we use this right-hand rule for the force on a wire in a magnetic field, the only difference is our finger is in the direction of L, where L is the length of the wire, and really it's the direction of the current. That's the key thing to remember there. Okay. One other thing, remember that if the charge is negative, if negative charge, you can either use the right hand and reverse your answer or use left hand. Currents are only one thing, so we don't have a second thing there. Okay, right-hand rule number two. That's giving you how to find the direction of the current, of the magnetic field created by a current in a wire. Okay, so this one is pretty straightforward. The magnetic field lines are circular. Remember, you need to be able to translate this to two-dimensional problems. So if I've got the current coming down there, put your thumb in the downward direction. If your fingers are on the left, you'll notice they're pointing in. And if your fingers are on the right of that wire and your thumb is still down, you'll notice they're coming out. So that's right-hand rule number two. Right-hand rule number three tells you how to find the direction of the magnetic field created by a current-carrying loop of wire, and it's only the direction inside the loop. So put your fingers in the direction of the current around the loop. Look where your thumb is pointing. If it is a clockwise current like this, notice that your thumb is pointing in. If I have another loop and it is a counterclockwise current, notice if you put your fingers in the direction of the current, your thumb is pointing out. Okay, so those are our three right-hand rules. Let's look at a couple interesting applications of what we've been talking about. So these are great engineering examples. Remember that engineering is basically taking the rules or the laws of physics and finding out interesting things that you can do with them, interesting products that you can design. So we know fundamentally that if you put a current-carrying wire in a magnetic field, it will experience a force where the magnitude of the force is ILB sine theta. Well, it turns out that this is how a speaker works. Basically, what we have to be able to do with a speaker is take some electrical signal, that represents some music or talk, and we need to change that back into a sound wave. Well, the way a speaker does that is we have what's called the voice coil of a speaker. It's a coil of wire in the back of the speaker. So if I were to view the speaker like this, what I would see is a coil of wire that is attached to this paper cone. And then the paper cone is loosely attached here at the frame so the cone can move in and out. So now what we do is we take that coil of wire and we put it in a magnetic field. So here you can see it's kind of like a three-dimensional horseshoe magnet. We've got a north pole in the center and it's surrounded by a south pole. If you were to look at this magnet from the top, it would look like this. There would be a gap. That would be the North Pole. There would be a gap, and then everywhere around it would be the South Pole. Okay? So it's in this gap where the coil fits. So think about what would happen if we put in a current that looks like this as a function of time into that coil. Well, we would have a current that is changing direction and changing strength in that coil. Well, if the magnetic field is either up or down and the current is either in or out, what that's going to give us is either a force out or a force in on the speaker. And what will happen is, since that force will be directly proportional to the current, the force in and out on that speaker cone will mimic the current, and therefore it will produce a sound wave proportional to the current. And so if you could watch a speaker in slow motion, you would see it simply moving in and out in response to the current that we put through it. Another example of a practical application of our formula that the force on a wire in a magnetic field is ILB sine theta is a DC motor. So DC motor means a motor that works when I connect it to a DC power source like a battery. And basically all a motor is it is a loop of wire that is placed inside a magnetic field. So you'll notice in this case we've got a magnetic field. Remember that magnetic fields go from north to south. So usually, or oftentimes, this is actually just one big horseshoe magnet, that comes around like this. But in other words, we're just showing the North Pole here and the South Pole here. So the magnetic field across this gap is to the right. Notice that if we put current in the direction shown in the diagram, that the force on this side of the loop will be down, and the force on this side of the loop will be up. And you'll notice that the net force in the loop is going to be zero, but what there will be is a torque. There will be a turning action of that loop. And so the more current we put in, the greater the force will be. So again, the force is going to be proportional to the current as well as to the magnetic field, and that loop is going to start spinning. Now, the one thing about a DC motor is that once it spins halfway around, it would actually flip back the other way unless we change the direction of the current in the loop. And so the detail here of the motor is shown here. It's called the commutator. And what happens there is you'll notice that we have this split ring so that every half turn of the motor, it changes which side is getting the current going in like this, so that always this part of the loop will have a current in this direction, so it will always experience a force down, and always the part of the loop that's over here will have a force up, and therefore we get a constant spinning. Okay, so DC motor, just a very simple application, well, not a simple application, but an important application of the fact that if you put a current carrying wire in a magnetic field, it experiences a force. Okay, let's remember Gauss's law. Again, we spent a whole chapter on this, so hopefully you remember it pretty well. You may remember at the time that I said this was the first of 4 equations that we call Maxwell's equations. And really one of our key goals in the whole course and in the brief time of the course that we have remaining is to understand Maxwell's 4 equations and how they predict the existence of electromagnetic waves. So just to remind you, the left-hand side of Gauss's law is called the electric flux. And remember that it's really just the mathematical way that we describe the number of field lines leaving through a closed surface. And we've said that the number of field lines is related to the number of charges or the amount of charge enclosed. So the flux is equal to the charge enclosed divided by epsilon naught. Notice too that field lines always start and end on electric charges. Okay, so that's important, and that's why if we have charge enclosed, if we have a net charge enclosed, it means we either have to have field lines coming in or going out of the surface. All right, we're now ready to learn our second of Maxwell's equations. And our second of Maxwell's equations is Gauss's law for magnetism. Now, if we were in class, I would have had you try to guess this. But it turns out that on the left-hand side, what we have is just magnetic flux. Notice exactly equivalent to electric flux. Okay, so it's related to the number of field lines leaving or coming into a surface. Now, why is the right-hand side of Gauss's law 0? Remember, one of the important things that we said at the beginning of this chapter is that there are no magnetic monopoles. In other words, we never have just a north or just a south pole. So there is no such thing as individual magnetic charge. And so how does that show up in this case? You'll notice that there is no surface that you can draw where the number of field lines entering is different than the number of field lines exiting. Because unlike electricity, where you can just have one charge so that you get field lines coming out of the surface, well, you can't have that in magnetism. You always have a north and a south. So that even if I look inside the magnet, those field lines are still there. Okay? So we learned that magnetic field lines are continuous. They don't ever start or stop because there's no equivalent of electric charge for magnetism. There's no magnetic monopoles or magnetic charge. Okay? So the number of lines entering and exiting the surface always equals to 0. Okay. So these are the key things conceptually that I want you to know about Gauss's law for magnetism. On the final exam, I'll be asking you things like that. Okay, that's it for Gauss's law for magnetism. By the way, that's our second of Maxwell's equations. We're going to now actually move on to the third of Maxwell's equations. So this is number 3 of Maxwell's equations. And it's called Ampere's law. Ampere's law allows us to figure out the magnetic field created by a current carrying wire. Okay? And I often think of it as kind of equivalent to Gauss's law for electricity in the fact that fundamentally, what is Gauss's law for electricity is telling you? It's telling you that charges create electric fields. Say that 10 times. Charges create electric fields. That's what Gauss's law is telling you. Okay? Pause the video, say that 10 times. So, what is Ampere's law telling you? currents or moving charges create magnetic fields. Say that 10 times. Currents create magnetic fields. Moving charges create magnetic fields. Okay, you'll notice that we've got a circle on our integral here, just like for Gauss's two laws. Here, though, it means something a little different because you'll notice that here, this is not an area. It's not like flux. It is just a length or distance. And so we call this a line integral. It's not a surface integral. Here's what it's trying to get at. Basically, this is saying that if you integrate the magnetic field over some path, and there is a current passing through that path, then the integral of B dot dr is equal to mu naught times the current enclosed in the path. And probably the easiest way to make this make any sense to you is I'm going to show you an example where we use it. Now, one of the things that I want you to notice is that we want to use Ampere's law to solve for the magnetic field, but the magnetic field is stuck inside an integral. Hopefully that sounds familiar to you because that was the exact same issue we had with Gauss's law for electricity. And if you remember, with Gauss's law for electricity, we could only actually use it to solve for the electric field if we could find a surface over which the electric field was constant, so it could come out of the integral. And then we just have the integral of dA, which is just the surface. It's very similar the way we use Ampere's law. So, just like Gauss's law for electricity, Ampere's law is valid always, but it's only useful to find the magnetic field if we can find a path over which the magnetic field is constant. So in other words, if B is constant over the path, then the integral of B dot dr just reduces to B times the integral of dr, and that is just the length of the path. So the integral of dr is just the length of the path. And again, we'll do some examples so this will hopefully make a little bit more sense to you. What I have here is just a diagram to illustrate this. So for example, here we have a wire coming with a current coming straight towards you and another wire with a current coming straight towards you. The question is, could I use Ampere's law to find, the magnetic field at some point, like right here? And so here would be a possible path that I could go around. So, do you think I could use Ampere's law using that path to find the magnetic field right here? Well, hopefully you are saying no, because you'll notice that in order to use Ampere's law to find the magnetic field, it's got to be constant around that path. And it's clearly not, because here the magnetic field is crossing the path. Here it's kind of equally spaced from the path. It's not constant. We couldn't use Ampere's law to solve that problem. Well, let's do a problem that we can do with Ampere's law. Do you remember when we used Coulomb's law to find the electric field of a point charge? This is the kind of equivalent problem, which is we're going to use Ampere's law to figure out the magnetic field of a wire. Now, earlier in this chapter, I simply gave you the result. I told you that B was mu naught I over 2 pi r. But now we're going to use Ampere's law to show that. The one change I've done in writing Ampere's law here is instead of writing it as dr, I've written it as dl. That's just so we don't get confused because there's another r in this problem. So what do we mean by dl? dl is just a little piece of our path. So that's dl. And we're just making up our path by adding up little bits of path dl. Notice that dl and the magnetic field, we know the magnetic field lines are concentric around a wire, so there's our vector B. So notice that DL and B are in the same direction, and that's true no matter where we are, right? Because if we're looking at that little piece of path DL there, notice that B is also in the same direction. So the first thing that we always have to do if we've got a dot product stuck in here is we have to do the dot product. But that's just the magnitude of B, magnitude of DL, cosine of the angle between them. And again, in this case, we see that theta is 0. And so that cosine theta is just going to go to 1. Now, you'll notice that I don't know what the strength of the magnetic field is along my path, but the key thing is I've picked a path that always is the same distance r from the wire. So there's no reason that the magnetic field strength would be different anywhere along that path. That's how I get the B out of the integral. So now I just have the integral of dl. Well, what is dl? It's just these little pieces, and I want to add them all up around that path. Well, it's just the length of the path. Well, that's just the circumference of that circle, 2 pi r. So I've got B times 2 pi r. Now on the right, the current enclosed, there's only one wire inside my path that's carrying a current I. So I enclosed just becomes I. And now I just solve for B, and I get mu naught I over 2 pi r. And that is what I had told you previously. Let's get some practice using Ampere's law in another example. I want to figure out the magnetic field of a solenoid. The first thing I have to do is tell you what a solenoid is. A solenoid is basically a coil that is spread out over a length. So you can imagine if you took like a paper towel roll or something like that, and you wound wire on it, one loop after another, where they weren't overlapping, but they were stretched out along that tube. That's what it would look like. Here's a cross section of a solenoid. Notice it shows the current coming out and going in. But again, we're just talking about, something wrapped around like that. That's what we mean by a solenoid. Okay, so first of all, solenoids are important. They're important in a lot of engineering applications, which I'm going to talk about. The other thing about a solenoid is it's a quick way to create a magnetic field that's very similar to a bar magnet. You'll notice that if I drew a bar magnet, I would say that the magnetic field lines coming out of it look something like this. And if I look big enough, I can see them curl around. But basically, I've got very strong fields by the north and by the south pole, and the fields are leaving the north pole field lines and coming back towards the south pole. Notice that's exactly what the field looks like from a solenoid. So it's a quick way to create a magnetic field using electricity that's very similar to the magnetic field of a permanent bar magnet. Okay, so to figure out the magnetic field of a solenoid, specifically what we want to do is we want to figure out what is the magnetic field in here. You'll notice that it looks pretty constant. Those lines are sort of equally spaced. And we're going to try to figure out what is the magnetic field inside a solenoid. Well, the first thing that we need to do to figure this out is to understand that outside of a solenoid, if you're like here or here, the magnetic field is basically 0. So again, this is a picture of a cross section of a solenoid. Imagine you looked at the solenoid from the end and I cut it in half, right? So that's what we're looking at. Well, let's look at just the magnetic field coming out of the solenoid from this particular wire. Notice the current is coming towards us, so it's creating a magnetic field in this direction. Notice that I'm using right-hand rule number 2, thumb in the direction of the current, fingers give me the direction of the magnetic field lines. And if I draw a bigger loop there, you'll notice that looks like that. Okay. Now I want to look at the magnetic field of the current that's going in down here. We'll notice that my thumb is now pointing in. So if I draw my first loop like that, notice that it's going like this. And if I draw another of the field lines, notice again that it's going like this. What I want you to notice that inside the solenoid, the fields are adding. We get both from the bottom and from the top, we get a field going to the right. But notice that outside, they tend to cancel. This is going to the left, this is going to the right. This is going to the right, this is going to the left. And so what happens is, inside the solenoid, we get addition and we get a strong magnetic field. And on the sides of the solenoid outside, it basically kind of cancels out. All right, so now we are going to use Ampere's law to figure out the magnetic field inside the solenoid. And what I'm going to do is I'm going to figure out the left-hand side here first. And I'm going to do that by breaking down the path that I've chosen into 4 pieces. So the integral of b dot dr, remember what the closed loop means I have to start at one point, go along a path, and get all the way back to the same point on the path. Okay, so I'm going to break this down and say I'm going to first integrate from a to b of b dot dr. Then I'm going to integrate from b to c of b dot dr. Then I'm going to integrate from c to d of b dot dr. And finally integrate from d back to a of b dot dr. Okay, so let's figure this out. You'll notice that the first integral from a to b is outside the solenoid on the side. So what do you think that's equal to? What's this part of the integral equal to? Well, hopefully you all yelled 0, because outside the solenoid, b is 0. That's why we just talked about that. Okay, let's look at the next integral from b to c. Well, it turns out that that's equal to 0 as well. How do we know that? Well, because we know that b dot dr, that's a dot product. So inside that, we're really doing b dr cosine theta, where theta is the angle between b and dr. Notice that our path from b to c is in that direction. Outside, the magnetic field is 0 anyway, but inside, the magnetic field is that direction. So b dot dr equals 0 because b is perpendicular to dr. So that part of the integral is 0. Now from c to d, notice that dr, notice that we're going in the direction of the magnetic field. So you'll also notice that the magnetic field is the same everywhere in there. So I just get b times the integral of dr, and that's just going to be the length of my path, which I'm going to call L. So that's the first non-zero contribution that I've gotten. Notice that from D to A, that's equal for 0 for the same reason that it was from B to C. And therefore, what I end up with is just B times L. Okay, so that's the left-hand side of Ampere's law. We figured is B times L. We've now got to figure out what the right-hand side is equal to. So the right-hand side is the current enclosed. Again, we've got the integral of b dot dr is equal to mu naught I enclosed. And we figured out the left-hand side is B times L. The right-hand side is mu naught, but now we got to think about how much current is enclosed. You'll notice that there, all of those are wires with current passing through our path. So what we do here is we say, however many of those loops are passing through the path times the current that's in our solenoid, that's got to be the current enclosed. So N is the number of loops in the path. Now, oftentimes we write this instead as little n, where little n is the number of loops per length. So literally, if you had a solenoid, you can count how many loops there are, 1, 2, 3, 4, 5, 6, 7, per a given length. And so we write that as little n, that's the number of turns or number of loops per length. And so if we write this as B is equal to mu naught N over L times I, we can rewrite it, and our final answer is mu naught N times I. So we've used Ampere's law to figure out that the magnetic field inside a solenoid is just equal to mu naught times the number of turns per length of the solenoid times the current that you put in the solenoid. And so if you need a nice constant magnetic field, you can find that inside a solenoid. Let's go ahead and try out the following problem. It says, find the magnetic field inside a solenoid 20 centimeters long with a total of 100 turns, carrying a current of 3 amps. So we figured out that the strength of the magnetic field is mu naught times N times I, where mu naught is our constant of magnetism, 4 pi times 10 to the negative 7th. And so in this case, we know that we've got 4 pi times 10 to the negative 7th. Now for the number of turns per length, here we know that there are 100 turns in a length of 0.20 meters. So that would be little n. And then times a current of 3 amps. And what we find is that the magnetic field inside our solenoid would be 1.9 times 10 to the negative 3 Teslas. Let's talk about a really important practical application of a solenoid. And that's actually what's often referred to as a solenoid in engineering applications. But really usually when engineers are talking about a solenoid, they actually mean a physics solenoid, in other words, our coil, with an iron rod and a spring. And so what I want you to think about is, let's say that you would like to just push a button and have something mechanical happen, where there are basically two things that you might want to have happen. You might want something to move linearly, in which case you use a solenoid like this, or you might want something to spin, in which case you'd use a motor like we talked about previously. So here's how a solenoid works. Here is our coil of wire. We have it connected to a battery and a switch. And here we have a metal rod that has a spring that holds it in its normal position. Well, here's what happens. When I close the switch, I energize this coil. Well, we know that that creates a strong magnetic field inside the coil, and that will actually attract the iron rod, and the iron rod will come out into the coil. Now, when I open the switch, the spring pulls the rod back into place. So I now have a mechanical device that will have two different positions based on how I operate an electrical switch. Let me show you two places where solenoids are used. The first one is kind of a goofy example, and the next one is a really important example. Here's the goofy example, a doorbell. If you want a bell to ring when you push a button, this is exactly what you need. You've got your solenoid here, so iron rod, spring, and actual coil of wire. You'll notice that when you push the button, close that switch, it's going to pull the metal bar into here, and it's going to hit the bell, and you're going to get a ding. By the way, if you want not just a ding, but you want a ding and a dong, you let your rod come out the other side, and you have a second bell here. So when you push the switch, the rod comes in and hits the bell. The rod stays in there as long as the coil is energized. When you let go of the switch, the spring pulls the rod back and hits the other bell. And I've actually taken apart doorbells that work exactly like this. So that's how you get that ding dong when you push the button and let go of the button. All right, let's look at a more important application, and that is a car starter. So when you go out to your car and you turn the key, or if you've got a push button start, you push the button, an electric motor engages with your gas engine and starts spinning it until the gas engine fires up and starts to run. So if you think about what we've got to do there, we've got to temporarily connect an electric motor, spin the gas motor, and then disengage from it. So this is what a starter motor looks like on a car. We've got this part is the actual electric motor, which again, you guys know how an electric motor works now. And this is the solenoid. What the solenoid does is it pulls a lever into it. So here's where the coil of the solenoid is. It pulls the iron level in, and what that does is through a pivot, it pushes this gear out and into the flywheel of your engine. And then, so when you've got your key in the start position, the solenoid is engaged. It pushes this gear into the flywheel of your engine, and then the electric motor starts turning the engine. As soon as you let the key go and it goes just back to the run position, that de-energizes the solenoid, the rod gets pulled back out by the spring, and this gear goes back in and out of the flywheel of your engine. So if you've ever had the situation where you turn the key and it just clicks, that can be either because you have a bad solenoid on your starter, or the battery is dead enough it won't engage the solenoid so that the starter engages and starts spinning the flywheel. Okay, so the key thing to remember is this idea of a solenoid is used anytime you want something mechanical to happen based on an electrical signal. Another really goofy example, inside your dishwasher, there's that little door that you put soap in and close it, and then magically somehow during the process that door gets opened. That's a little solenoid in your dishwasher that when it gets the electrical signal, it pulls the little pin back and opens that door. All right, let's summarize what we've learned in this chapter, because we've learned a lot. This is the kind of conceptual understanding I want you to have for the final exam. So, how many times have we said this? Electric charges create electric fields. And if you put a charge in an electric field, it experiences a force. So now we know the equivalent for magnetism. There is no such thing as magnetic charge. There are no magnetic monopoles. If you want to create a magnetic field, you need moving electric charges. Moving electric charges create magnetism. So that means anytime you have a current in a wire, it's creating a magnetic field. Here's the magnetic field created by a straight wire. We also know that moving charges will experience a force if placed in a magnetic field. So either individual charges create a magnetic field, or experience a force in a magnetic field is given by that formula. Or if it's instead it's a current, then that in a magnetic field experiences a force. Okay? So moving charges create magnetic fields. A moving charge in a magnetic field experiences a force. Okay? So make sure that you understand this table. Okay, another important table to summarize the other things that we talked about in this chapter. Electric fields are created by charges, as we've just talked about. Well, Gauss's law allows us to figure out what the electric field is created by a charge distribution, as long as it's symmetrical enough that we can get E out of that integral. Well, now notice we have a similar relationship for magnetism. That's Ampere's law. Remember that it tells us that currents create magnetic fields just like charges create electric fields. But again, it's only useful in pretty symmetrical situations because we've got to be able to get B out of the integral to actually solve for it using Ampere's law, just like we had to get E out of this integral. There are more general ways to calculate electric or magnetic fields when we can't use Gauss's law or Ampere's law. And again, that's what we talked about in the chapter. Okay, so these last two slides are important because it really emphasizes the concepts behind what we've been talking about.